After detecting an unusual wobble in space, astronomers were led to a new discovery in our own Milky Way, the massive stellar black hole known as Gaia BH3. This monstrous entity is located about 2,000 light-years away in the constellation of Aquila, the Eagle. Despite clickbait headlines, this distance assures us that Gaia BH3 poses no threat to our solar system. 2,000 light-years away is 2% of our galaxy's total span of 100,000 light-years. So it's safe to say this black hole won't devour Earth just yet. In fact, Gaia BH3 isn't even our closest black hole. That title belongs to Gaia BH1, which lurks a bit nearer at 1,500 light-years away. However, what sets Gaia BH3 apart is not its proximity, but its sheer mass. It is the most massive stellar black hole ever discovered within our galaxy. This revelation came through data from the European Space Agency's Gaia mission, which was launched in 2013 with the mission to create a 3D map of 1 billion stars. As researchers were reviewing the Gaia observations, they noticed a distinct wobble in one of the stars in Aquila. The movement suggested the star was being pulled around by a black hole 33 times more massive than the Sun. To put that into perspective, consider our Sun, which weighs about 2 times 10 to the 30th power kilograms. That is 2 followed by 30 zeros, or 2 nonillion kilograms. Now imagine the combined mass of 33 suns compressed into an incredibly dense point in space. That's the staggering reality of BH3. A mass so large, it bends the fabric of space itself, creating the observable effects that led to its discovery. Apart from the central black hole in the Milky Way, BH3 is the heavyweight champion of known stellar black holes in our galaxy, and it ranks as the second nearest ever discovered. Further observations from the Very Large Telescope in Chile confirmed BH3's mass and the star's orbit, which circles the black hole once every 11.6 years. Measurements of BH3's companion star found no sign that it was contaminated by material from the cataclysmic supernova that likely birthed the black hole. This suggests the black hole formed long before it trapped the companion star in its powerful gravitational field. The companion star itself is an ancient giant, believed to have originated in the first 2 billion years after the Big Bang. The star's trajectory, which moves in the opposite direction of many stars in the galactic disk of the Milky Way, suggests it was part of a small galaxy that merged with the Milky Way more than 8 billion years ago. Now the team of researchers hopes their work can allow other astronomers to study the colossal black hole and uncover more of its secrets without having to wait for the rest of the Gaia data to be released in late 2025. We have only seen black holes of this mass through gravitational waves in faraway galaxies. Scientists think there may be as many as 100 million stellar black holes in the Milky Way, but despite their mass and the powerful forces they generate, they can be extremely difficult to detect. Most don't have companion stars that reveal their presence, so they are almost invisible to us. Stellar black holes form by the gravitational collapse of a star, which is to say when massive stars die. They are the remnants of supernova explosions, which may be observed as a type of gamma-ray burst. These black holes are also referred to as collapsars. So Gaia BH3 is the most massive black hole in our galaxy that formed from the death of a massive star. On average, stellar black holes in our galaxy weigh in at about 10 times the mass of the Sun. Before the discovery of BH3, the record holder was Cygnus X1 with 21 solar masses. While Gaia BH3 is an exceptional find within our galaxy, by astronomers' standards, It is similar in mass to objects found in very distant galaxies. Scientists think that stellar black holes formed from the collapse of metal-poor stars. These ancient stars, primarily composed of hydrogen and helium, the lightest and most basic elements, tend to lose less mass throughout their lifetimes. This retention of mass sets the stage for the formation of larger mass black holes at the end of their stellar life cycles. Astronomers hadn't been able to find evidence directly linking high-mass black holes and metal-poor stars until they found Gaia BH3. The gravitational collapse that leads to the formation of black holes is an inevitable end for massive stars once they exhaust all nuclear fuel. Depending on the mass of the collapsing core, the outcome can be a compact star, such as a white dwarf, a neutron star, or even a more exotic quark star. However, if the core's mass surpasses what is known as the Tolman-Oppenheimer-Volkoff limit, it will continue to collapse to a singularity, forming a black hole. The precise upper mass limit of a neutron star, before it collapses further into a black hole, is not fully understood. But in the theory of general relativity, a black hole could exist of any mass. But there is a catch. The lower the mass, the higher the density of matter must be to form a black hole. There are no known stellar processes that can produce black holes, with mass less than a few times the mass of the Sun. If black holes that small exist, they are most likely primordial black holes. In a recent 2020 study, astronomers observed a binary star system made up of a giant star and its mysterious small companion. It was reported that this companion is the smallest mass black hole currently known to science, with a mass of 3.3 solar masses and a diameter of only 19.5 kilometers. To put this extreme density into perspective, we discussed earlier that our Sun has a mass of about 2 non-Illian kilograms. That is equivalent to the mass of about 333,000 Earths. To simplify this, we can imagine the island of Manhattan in New York City. So now imagine more than 1 million Earths squished together into a sphere, just 19.5 kilometers across. This extreme density shows the truly mind-boggling nature of black holes, demanding further exploration into these freaks of nature. There is observational evidence for 2 other types of black holes that dwarf stellar ones: intermediate mass black holes, located at the centers of globular clusters, and supermassive black holes, which reside at the centers of galaxies including our Milky Way. The process by which supermassive black holes form is not fully understood, but one theory suggests it happens when massive cosmic clouds of gas and dust collapse. At the galactic center of the Milky Way lies the supermassive black hole known as Sagittarius A star. Situated approximately 26,000 light-years from Earth, it holds about 4.3 million times the mass of our Sun. Its immense gravity anchors the galactic fabric of the Milky Way, which itself weighs as much as 1.5 trillion solar masses. The angular size or apparent diameter of Sagittarius A star is calculated to be close to 52 million kilometers, while its Schwarzschild radius is 12 million kilometers. To visualize this, imagine a dark sphere with a diameter of 24 million kilometers, or about 17 suns wide, containing the mass of 4.3 million suns. That's what's happening at the center of our galaxy. But how do these cosmic giants grow so big? In 2004, a team of astronomers reported the discovery of a potential intermediate mass black hole, orbiting only 3 light-years from Sagittarius A star. This black hole of 1,300 solar masses is within a cluster of 7 stars. This observation may add support to the idea that supermassive black holes grow by absorbing nearby smaller black holes and stars. Yet even Sagittarius A star pales in comparison to the true king of size of supermassive black holes, in TON 618. This is considered one of the highest masses ever recorded, higher than the mass of all the stars in the Milky Way galaxy combined, which is 64 billion solar masses and 15,300 times more massive than Sagittarius A star. A black hole of this mass has a Schwarzschild radius of 1,300 astronomical units, which is more than 40 times the distance from Neptune to the Sun. The mass of 64 billion suns is incomprehensible, and with such humongous mass, TON 618 may fall into a new classification of ultra-massive black holes. The universe is truly mind-boggling and stranger than we can ever imagine. Thank you for watching.